Hi everyone, my name is Shiqiu, and today I want to talk about a critical aspect of software security, API misuse detection. And today we are using OpenSSL as an example. So, OpenSSL is a workhorse for implementing protocols like TLS and SSL, which secure countless web connections, VPNs, and other applications. Its power comes from a rich but notoriously complex API. This complexity, combined with documentation that can sometimes be opaque, creates a fertile ground for errors. Developers, often under pressure, might copy code snippets, misunderstand parameters, or overlook crucial configuration steps. And the consequences of these mistakes aren't trivial. An improperly configured SSL context might fail to validate server certificates, and opening the door wide for man-in-the-middle attacks where an attacker can intercept and even modify sensitive communication. Using outdated cryptographic algorithms, weak keys, or predictable random numbers can render encryption ineffective and potentially exposing confidential data. These aren't theoretical concerns. Numerous high-profile vulnerabilities have stemmed directly from OpenSSL API misuse. Therefore, the central question we are addressing is, how can we reliably and efficiently find these potentially devastating misuses before they cause harm? We need detection methods that are not only effective in finding potential flaws, but also accurate enough to avoid overwhelming developers with false alarms. So, what kind of mistakes are common? Just briefly, on the protocol and configuration side, we often see issues like selecting weak cipher suites, think RC4 or old DES algorithms. Developers might also use deprecated functions that enable outdated protocols like SSL v3, or they might explicitly allow old protocol versions like TLS 1.1. Other examples include mishandling TLS renegotiation unsafely, or performing incomplete quiet shutdowns that risk data truncation. These are just typical examples of configuration errors that can compromise security. Similarly, in core crypto operations and basic error handling, misuses often occur. This includes directly calling functions for known weak ciphers like RC4 or DES. A subtle but critical error is disabling standard padding for block ciphers, which breaks security assumptions. And using RSA without proper padding is another classic mistake. So again, this is just a sample to illustrate the kinds of problems that arise when using these complex APIs. So, how do we typically find this problem today? One common way is static analysis. These tools examine your source code or compiled files directly without running the program. They look for patterns matching predefined rules that suggest potential misuse, like calling a specific risky function or using a known byte value. Think of tools like CryptoGuard or CodeQL queries. And the main benefit is coverage, right? So static analysis can scan the entire code base relatively quickly and find issues early in the development cycle. But static analysis isn't perfect. Its biggest issue is often false positives. Since it doesn't know the program's runtime state, it flags many things that aren't real problems, and creating noise that developers have to sift through manually. It can also miss things, like false negatives, if its rules aren't comprehensive or if the code's logic is too complex for it to understand fully. So, when coverage is good, the accuracy can be a significant challenge, leading to wasted effort. And another approach is dynamic analysis, which monitors the program while it's running. So it watches the actual OpenSSL function calls, the parameters used, and the results. Techniques often involve hooking into these function calls using methods like LD preload or frameworks like FRIDA to observe the behavior live. So the key advantage is high accuracy. If dynamic analysis reports an issue, it almost certainly happened during that run, meaning very few false positives to deal with. Dynamic analysis also has limitations. Its main challenge is coverage. It can only find problems in the code path that actually get executed during the test run. If your tests don't trigger the faulty code, the issue remains hidden. Achieving good test coverage can be difficult. There's also potential runtime overhead from the monitoring, and setting up the necessary hooks can sometimes be more complex than running a static analyzer. So basically, you are trading coverage for accuracy. So, we've seen the trade-offs. Static analysis provides broad coverage but suffers from high false positives and thus making it noisy. And dynamic analysis offers high accuracy but struggles with code coverage and making it potentially narrow in scope. So neither approach alone is ideal. Static analysis overwhelms developers with potential non-issues, and while dynamic analysis makes real problems lurking in untested code paths. So this leads us to the central idea of our project. Why not combine the strengths of both? We can leverage the broad reach of static analysis to identify potential areas of concern across the entire codebase. Then, we can use a high precision or dynamic analysis to verify whether these specific flagged warnings actually manifest as programmatic behavior during runtime. Our solution, therefore, is to develop a dynamic verification tool. This tool isn't intended to replace static analyzers, and instead, it acts as a smart filter. It takes the list of warnings generated by a static analysis tool as input, and then it monitors the application's execution, specifically focusing on the code locations and API calls highlighted by the static analysis report. By observing the actual parameters and return values at runtime, it can confirm which static runnings correspond to real observed misuses and which one did not. So this hybrid approach aims to deliver the best of both worlds: broad initial scanning followed by accurate, context-aware verification. Let's define the goal and technical design of our dynamic verification tool more concretely. The primary objective is to create a lightweight and practical tool that integrates with the output of existing static analyzers. So its core function is to take a list of potential OpenSSL API misuse warnings and, by monitoring the application at runtime, determine which of these warnings represent actual verifiable misuses occurring during execution. The key outcome is a filtered list of warnings, significantly reducing the number of false positives and developers need to investigate. To achieve this, while keeping the implementation manageable, we've chosen a specific approach. We are targeting Linux environment for now. So the runtime monitoring will be implemented using a C++ hooking library based on LD preload. This technique is relatively straightforward to implement for intercepting calls to DLLs like OpenSSL. And it allows us to write custom wrapper functions for specific APIs. These wrappers will capture relevant arguments or state changes and log them. The overall control, data processing, and analysis logic will be handled by a Python script. This script will be responsible for parsing the input static analysis report, launching the target application with the LD preload library injected, and collecting the runtime logs generated by the hooks, performing the matching logic between logs, events, and static warnings, and finally generating the output report. This combination leverages C++ for efficient, low-level interception and Python for flexible high-level orchestration and data handling. So this diagram illustrates the high-level architecture of our dynamic verification system. Let's walk through the components and data flow. On the far left, we have the input, which is a report generated by an external static analysis tool, and typically in a structured format like JSON or XML, containing a list of potential OpenSSL misuses with details like the function involved and code location. The input is fed into our dynamic checker core, implemented primarily in Python. The static parser module reads and understands the input report. The main orchestrator, or checker.py, will then launch the target application, the C program we want to analyze. Critically, it launches it using LD preload to inject our hook library here. And as the target application runs and makes calls to OpenSSL APIs, the preload hook library intercepts its calls using its specific hooks. And information about these calls is recorded by the logger component within the library and generating runtime logs. After the target application finishes, the measure module in Python will read these runtime logs and compare the logged events against the parsed information from static analysis results, or the input. It will determine which static warnings were observed dynamically. And finally, the reporter module makes the results from the measure and generates the final report. This report categorizes the original static warnings into found and not found groups, and this final report is a primary output for the developer or user. Alright, theory is one thing, but let's see the action. I'm now going to demonstrate the dynamic verification tool we built. For this demo, we'll use a simple C program that intentionally includes a couple of common OpenSSL misuses we discussed earlier. It might also contain correct usages. We'll assume a static analysis tool have already run on this code and produced a report. What you are about to see is our dynamic verification tool taking that hypothetical static report as input. We will then run the vulnerable C program with our LD preload hooks active. Our tool will monitor the OpenSSL calls made by the program in real time, and the key things to watch for is the final output report generated by our tool. We expect it to confirm that the misuses we've written were indeed observed during the execution, thus marking them as verified. And other static warnings that didn't correspond to runtime behavior would ideally be flagged as untriggered, helping us to focus on the real issues. Okay, now let's see the live demo. Okay, so first let's see the sample static results before we begin. So this is a static result example. It's written in JSON. And as you can see, they have a description, function, and condition. So for example, for this one, this indicates that the user is using a weak hash algorithm like MD5, and the second one is SSL certificate verification disabled. And in this rule, the developer is calling this API using these parameters. So like these are all the rules here. And then we can see the source code. It's divided into three parts. The first one is the checker core, which parse the JSON file and execute the code. And then we have a hook lab, which there are multiple hooks. So each of the hooks will listen to one of the OpenSSL APIs. For example, this hook will listen to this API, and there are 12 hooks which corresponding to the 12 rules over here. And then in the last we have a web app. It's a very simple one. I will demonstrate later. So first we can begin with compile the hook lab. Let's just execute make. So I've already written all the necessary make files here. So only one make should compile everything. So we now have, we have three code examples to demonstrate the problematic OpenSSL usage. The first one would be weak hash example. It's using MD5. The second one is disabled SSL certificate verification. And in the last, we have a comprehensive test that calls nearly all the rules here. So there will be 3 examples. And let's first let's then build the checker core. Like I have already got this checker core as a Python package that users can install. So just by executing pipe install, and it will install the dynamic checker into the user's Python environment. So just by typing OpenSSL checker, yes, as you can see, we have the code installed. So now let's execute the first example. So of course we need to say like we are using this sample result.json, and then what we want to execute is the let's say for example this MD5 example. Oh, sorry, a typo. OpenSSL checker. Yes, and execute complete. So the code will generate a final report in Markdown. And as you can see, we have one rule confirmed, and the other 11s are false positives because they are not existent in this example. And now let's run another example. Let's run the SSL one. Okay, so the SSL again, we have confirmed one issue, and there are 11 false positives. And again, you can see actually in the hook log, we have 3 hooks successfully interpreted, but the other 2 hooks are just ordinary calling. Like for example, for this one, it's using SHA-384, which is a relatively secure algorithm, so it's not seen as an error. So it is not in the final report. Okay, so this is the console usage. Now let's see the web app. Let's first run the web app. I think it's source code webapp.py. And yeah, it gets a report. So here is a very simple web app. As you can run dynamic checker on a executable. And for example, let's run this this one. Copy path. Let's copy it to here, and we say working directory. So the program will generate all those logs and reports into the working directory. So it depends on where you want to save your reports. So we're running with no arguments. So let's run the checker. And yeah, as you can see, the final report, which is Markdown, is parsed and rendered well in this web UI, and you can see std out and std error in this here. So we have 10 rules verified, and we have 2 false positives. Yeah, so that's all for the live demo section. Okay, so this is what we have achieved with this approach and tool. The most significant benefit is improved accuracy in misuse detection. By dynamically verifying static analysis warnings, we drastically reduce the number of false positives that developers have to sift through. This saves considerable time and effort, making the entire process of finding and fixing security flaws more efficient. This directly leads to a better focus on real risks. When developers receive a filter report highlighting issues confirmed by the runtime execution, they can trust the findings more and prioritizing fixing these verified vulnerabilities, rather than getting lost in a sea of potentially irrelevant warnings. So this helps ensure that the critical security holes are addressed promptly. And furthermore, the project delivers a practical prototype of a tool that implements a hybrid static dynamic verification methodology. So the architecture using LD preload and a Python orchestrator provides a feasible and relatively easy to understand framework. It's also extensible. New hooks for different OpenSSL functions or misuse patterns can be added to the C++ library, and the Python core can be adapted to parse outputs from various static analysis tools. And finally, working on and demonstrating this tool helps in enhanced understanding. It highlights the practical challenges and showcases how different techniques can help each other. It promotes a better view of security tooling. To wrap up, we have explored the common pitfalls associated with using the OpenSSL API and the pros and cons of static and dynamic analysis methods for detecting these misuses. Our key takeaway is that while static analysis offers a broad coverage and dynamic analysis provides high accuracy, neither is sufficient on its own. Our work demonstrates that combining dynamic verification with static analysis presents an effective and practical strategy. By using runtime monitoring to confirm or refute the warnings generated by static tools, we can significantly enhance the signal-to-noise ratio, providing developers with more actionable security insights. Our prototype tool successfully implements this concept using LD preload hooks and Python scripting. Looking ahead, there are several avenues for future work. We can expand the coverage by implementing hooks for a wider range of OpenSSL APIs and encoding detection logic for more complex or subtle misuse patterns. We could also improve integration by adding parsers for the output formats of various popular static analysis tools, making the verifier more versatile. Enhancements to usability and performance are always possible, perhaps by optimizing the logging mechanism or providing a more sophisticated user interface than the current UI. Lastly, exploring more advanced hooking techniques like FRIDA could offer greater flexibility and potentiality, easier development across different platforms or for statically linked targets, and investigating techniques like guided fuzzing could help improve the runtime coverage needed for the dynamic verification phase. So that concludes my presentation. Thank you very much.